I want to talk a bit about communication which involves dissemination. And I have to admit this, years ago I started to work on gossiping protocols or epidemic protocols, and they are so cute. And I had to throw this in. And actually I think at that time it was a bit exotic, at least the way that I did it. But by now actually gossiping protocols are becoming more and more important because they are so simple that you understand them, and they are extremely robust. So you actually see information dissemination through gossiping as an important mechanism in distributed systems. I'll just tell you a bit about what this is all about. Okay, I'm going to make a few simple assumptions. There are, for one, no right-right conflicts. That really simplifies matters. So imagine a big distributed system. You do not have two processes trying to insert an update at the same time. Everything is, let's say, serialized through one process. This is not an unrealistic assumption, by the way. And the model that you should have is that I have a huge number of servers, and my problem is I want to make sure that an update reaches all those servers. Okay? That's it. That's my only concern. So update operations are performed at a single server. All these servers are connected through an overlay network. I will build a very specific one. It will change all the time. A server will just select another server at random and then pass some information onto that one. So a replica or a server passes updated state to only a few neighbors. Update propagation is lazy. This is something that I assume can be done or is affordable. So you don't have very strict real-time constraints on propagating updates. It's like, okay, here's an update, just make sure that eventually the update reaches all servers. Later when we talk about consistency, I'll make a claim that eventual consistency is actually a very important concept in very large-scale distributed systems. So indeed, eventually, every update should reach every replica. Now, there are essentially two forms of epidemics. It's called anti-entropy and gossiping. Anti-entropy comes from the following. What you do is essentially this. You take this room, let's say I want to propagate an update. So I blindly pick one of you and say, let's exchange data. And the data exchange is like this. You give me all new stuff that you have, and I will give you all the new stuff that I have. And now a very important observation. After the exchange, you and I have exactly the same information. Got it? So if you realize that entropy is generally a measure for chaos, we start in a completely chaotic situation, but after you and I have exchanged information, we have exactly the same information. I'm reducing chaos. That's the reason why it's called anti-entropy. Now what you need to realize is that everybody has this behavior. So you would also be picking someone else at random, exchanging information. In the meantime, I will be doing this again. And within no time, everybody is exchanging information like hell. And I will make clear in a minute that you have no idea how quickly updates are propagated in such a system. Okay, you had a question. Okay, that's anti-entropy. Gossiping, which is actually much nicer to explain, works like this. You have a server, it has just been updated, and what it does, it tells a number of other replicas about its update. Okay? And I'll zoom into that in just a bit. Yes?
So this is just like RIP over VPN?
This is just like RIP over VPN. RIP is not just rest in peace. It is the... what was the R again? I forgot. Routing Information Protocol. Thank you very much.
It's except for the picking at random part, but the
Well, that's the important one over here. Can you keep that question for just a minute? Because I want to make so it's yes or no. You can drop the VPN part. It is similar to protocols like RIP, notably the Bellman-Ford protocol, which is basically, you could argue, a form of a gossiping protocol by which you gradually discover what the network looks like, or actually how to find a path from A to B.
you have a direct mapping of the entire.
Yep. Yeah. But there's a fundamental difference, and maybe you'll be able to see the difference after I did the explanation. Okay. Let's first take a look at anti-entropy. This is basically what I just explained. What you have is that a node P selects another node Q from the system at random. This is very, very important. Just another one. And then you have a couple of modes: push, pull, or push, pull, push, pull, or push, pull. And this is awkward. Okay, so push is like I contacted you. I say here's my stuff. Okay. Pure pull would be I contacted you and I say, okay, just give me your stuff. You're not going to get anything from me. And push pull is that you really do the exchange. Turns out that just doing the exchange is a thing to do. Okay? And it turns out that for push pull, it takes order of log n rounds to disseminate updates to all n nodes. Okay? To all n nodes, yes. Now, what is a round? I'll be using that as a metric. So here we have it. There are, I think, approximately 100 people in this room. And we're all now processors, okay? And we behave in an anti-entropy way. So everybody has the following behavior. You pick someone, you do an exchange. And everybody does this, okay? Now, what is a round? Everyone has done tuck, tuck once. Okay? Exactly once. That's when a round is completed. And what I'm telling you, is everyone with me? Got it? Okay. So I can say, okay, guys, this, pick one, exchange, okay? And then, okay, hold it, let's do it again. And then every time we say, let's do it again, we enter a new round. If you do it like that, then it turns out that only in log n rounds, which is really not that much, an update will have propagated to everyone. Okay? So actually you could say that is real gossiping. And that's the reason why I will be a bit sloppy when I talk about epidemic protocols versus gossiping protocols. At a certain moment, I'll just say, hey, they're basically the same. Yes?
The updates originate somewhere, so why at time T0, time T1, everybody choose that number?
What? I will not repeat this question because I didn't understand. Okay? Yes?
You start the updates originates from only one node.
Oh, but everybody can have an update to tell.
Oh, okay. Then if it's only one, it doesn't make sense.
Yeah, okay, this is a good question. I'm assuming that if you have an update, that only one person will have an update on data item X. So you're responsible for data item Y, I'm responsible for data item X. I do the updates for X, you exclusively do the updates for Y. Okay? That's it. But even if nobody has updates, and I'm the only one having an update, log in. And with the login steps, everybody will know about my update by just gossiping. Most of the time, in the beginning, you'll be saying, got something new? No. Okay, neither do I. Okay? But this one person says, yeah, I just discovered something new. And this is how it goes. Tack, now you have 2 people disseminating my update. Then suddenly 4, 8, 16, 32. That's when you see overlap starting to come. But within no time, lots of people are participating in propagating my update. Got it? It's like a virus. So let's do a very simple analysis. It's really not that difficult. Now this is, by the way, not in the book. So consider a single source propagating its update. Let Pi be the probability that a node has not received the update after the ith cycle, the ith round. Okay? Don't worry, this looks like heavy-duty math. It's not, because I will tell you so. Just think along with me, okay? So in a pure pull mode, and let's just take one, just as an illustration. That's not that difficult. But it's more important that you understand that where the next graph comes from. So in pure pull mode, so that means contact you, say what do you have, and then I get something, okay? And PI is the probability that a node will not have received the update. Well, in the ith cycle. So what is then PI plus 1? Well, it's PI square, okay? Why? Because the node was not updated during the ith cycle, and I should contact someone who was also not updated during the ith cycle. So if I didn't have the update and you didn't have the update, I will not be updated in the ith plus 1 cycle. Agreed? Okay. So in pure pull mode, PI plus 1 is PI square. In PI plus 1, in the push mode, try to figure out yourself. No, actually that makes sense. Try to figure out yourself. It is exactly, it's a bit more difficult than the pure pull mode, but it's exactly the same. It basically boils down to this. I need to contact someone that is not going to give me anything. Okay? Nothing new. That's the trick. And then you'll easily come up with this part, and then just you have to happen to know that this is approximately like that for small PI. Okay? And then push-pull, you just combine the two. But try to do the push at home. You'll find it's not that difficult. This is what is more important. And I always forget how many nodes I had. I think 10,000 nodes. So I did a simulation with 10,000 nodes following this anti-entropy algorithm. Pick one, exchange. Okay? And then on the x-axis, I have the number of cycles or rounds. And here on the y-axis, I have the fraction of nodes that do not know about the update. I hope you're surprised or baffled or say, whoa, this is fast. So this is exactly what I just explained. In the beginning, most nodes will just, like in this group, will say, you got something new? No, I haven't something new. No. Nothing new to exchange. But as soon as you start spreading stuff, you get into this slope over here, and this is really fast. So as soon as you hit somebody who does have an update, you will be participating in spreading that update, and then it really is very, very fast. And then the tail behavior is, okay, there are some nodes out there that have not yet been, let's say, contaminated, okay? And you got to reach them. But now you get in the situation, pick someone, you have something new? No, you have it as well. Okay? Now you have to contact those nodes who do not yet have that update. So it slows down a bit. But it's still very fast. Is the idea clear? Okay. So you can see how much fun this is. This is so simple. If you would write the code for this, it would just be a few lines of Python code, for example. The data structures are more intricate than the code. This is so simple. This is so simple, it fits on a small wireless device with just 8K of static RAM. Okay? And we still have enough room left to log stuff and do other nifty things. Okay? So simple is this algorithm. So we do wireless gossiping in our research. Now, what is real gossiping? Okay, so I'll become sloppy in let's say 10 minutes from now, but not now. So there's a difference between anti-entropy and gossiping. What do you do with gossiping? You have a server, has an update to report, it contacts other servers. That's the whole idea. And if a server is contacted for which the update already has been propagated to, you stop. And this is you stop with the probability of 1 over k. K is a algorithmic design parameter, okay? And the model is really like this. It's a very social way of trying to spread news. So you're going to spread a gossip. I'm going to come. Have you heard the news? You say, no, good, I got a news. I give you the news, okay? And now, go, next one. Have you heard the news? You say, yes. Oh, shit. Okay? And I'm disappointed with the probability of 1 over k. If k is 1, and I phone you, you say, hey, I heard the news, don't tell me, okay? I stop. I'm disappointed, I stop. But if I'm optimistic, I say, okay. Let's say k is 2, 50% probability, I'm going to phone someone else. Okay? And then again, with a 50% probability, if that person did not hear the news, or hadn't heard the news, I'll stop. So I flip a coin every time I contact somebody who had already heard the news. Hey, how social can you get? Okay? You all recognize this model. Yes?
Is the probability decreases when I phone again and that person?
Probability is static. Okay, so k is really a static parameter. You choose it once for the whole algorithm. Okay. Now, if S is the fraction of ignorant servers, that means the ones who haven't seen the update, you can show that with lots of servers, you have this equation. This is a really, really nasty equation because you have an S over there and you have an S in the exponent. Okay? Don't solve it. Just use numerical analysis and it'll get you somewhere. And I have to change this picture. I want to give you an impression of what the relationship is between S and K. And again, I hope you're surprised. So what I did is, indeed, here's your 10,000 node network. If you follow the model that K is 1, so I phone you, you got the news, I'm disappointed, I stop. Okay? Now you really have to realize, if everyone has this behavior, so I phoned you, you didn't know the news. You're a happy camper. You're going to phone somebody else, right? And with only probability 1, you will stop when you bump into somebody who knew the news. Okay? What will happen, but I will stop. Okay? If I phone you, you've got the news, I stop. I stop completely. Which means that there's a risk that everyone will have stopped before the news has spread to everyone. That's what I'm talking about. That's this fraction S of nodes that remain ignorant. Okay? Because unlike in the anti-entropy case, you will stop in the gossiping case. That's the big difference. Got it? But watch out. Even with this probability 1, I phone you, you have the news, I stop. 20% of the nodes will not get the update. Only 20%. If k is 2, that drops to 6%. Okay, if I'm a bit more persistent, just look at these values for k. If k is 4, we're talking about 0.6% of the nodes in that entire network will not receive it. That's approximately 70 nodes in the entire network of 10,000 nodes.
And this only goes for one single update, right?
One single update. Okay? That's pretty good, right? Now, if you really need to ensure that everybody gets the update, pure gossiping is not going to work. Okay? So just combine it with a bit of anti-entropy and you're done. Would I be concerned about this? No, because they're all about statistics. So there are some really easy mechanisms to make sure that it really spreads to the full group. Okay? And there will always be one that may not receive it, but as I will argue at a certain point when we talk about fault tolerance or things can go wrong, at a certain point there will be a trade-off. Because, for example, if you have 10,000 nodes, there are so many other things that can go wrong. And the probability that those things go wrong will be much higher than the probability that you will not be able to disseminate your update. And then, hey, your whole attention shifts to these other problems. And that's the interesting thing when you think about really large-scale systems. There's always something wrong. And you just have to make sure that you prioritize on what you're going to pay attention to, or to what you're going to pay attention to. Okay? And this graph is a stupid one because it just shows that there is a logarithmic relationship between K and S. I shouldn't have done this. It should be this exponential curve that really shows, hey, for small values of k, it really drops rapidly. Okay, just look at the table. The table is more interesting. Okay, so we all agree, my God, you can spread the news like hell. Let's get news out of the network. Now you got a problem. Okay, so how do you delete a value? Well, you don't. You cannot. It's very, very difficult. So just imagine I have just spread a rumor through this room. Oh my God. I did something wrong. Okay? And I'm not one of these BBC guys who has to throw off his jobs because I spread a rumor which was wrong. Okay? So you cannot simply remove an old value. Let's just take a look at the anti-entropy case. You cannot remove an old value from a server and expect that removal to propagate. You can't do that. It's very simple. Let's say, oh, okay, well, everybody have the update, remove the update. So you remove an update.
Send out a new update.
Hold it. So you remove the update. You get contacted by your neighbor. It says, hey, I got something that you don't have. What is it? It's this old update. Here you have it. You got your update again. You see this work? So there's only one thing you can do. You can send an update saying, hey, what you got over there is outdated, which is a special type of an update saying, I'm done. Here's my death certificate. That update is old. Will you please keep the death certificate? Okay. So you can register a removal by means of a special update, which we call a death certificate. Yes?
You could also just wait like 20 iterations, right? And then do the new update.
We'll come back to that in just a minute. Okay.
How do you distinguish from an update which death certificate comes after that? The updates are...
Oh, okay, yeah. So how can I distinguish... Yeah, so how can I distinguish... So a death certificate is a special update. So imagine that my update, my pre-death update, reaches a node that had already received the death certificate. I like this question a lot, by the way, because you are exposing one part that I haven't discussed, namely, I cannot say in which order updates arrive at nodes. But let's make the assumption that I can distinguish updates by order by attaching a sequence number. Then that would save the day. And this is not an unreasonable assumption, because I'm the single source of updates, including the death certificate, so I can timestamp them, but not even with a time value, but just a sequence number, and then you will see you get your death certificate, and then a update that was actually propagated before the propagation of the death certificate comes in, and the death certificate will overrule that update. Okay? Yes?
But you could just prevent that by waiting 20 years.
Keep that question to you. We'll get back to that later. And just in a minute. Yes? If you would have multiple sources for updating, you have a very big problem. Oh, sorry. What if you would have multiple sources of updates? That's what's basically your question, right? Well, you would have a very big problem. And the problem was so big that I said, I'm going to assume that there's only one server, one source per update. You and I are not allowed to send updates for the same data item X. That was my assumption. I'm serializing all updates through a single owner of a data item. Okay? Otherwise, you'll just have conflicts. I'm not going to get into conflicts right now. Okay. So, you got to keep your question, okay? Because this, you'll have to use that question here. So, good. Now I'm spreading death certificates. I want to get rid of death certificates, right? Because, hey, I just declared basically a data item as, throw it away. Nobody's used it. And I got to keep my death certificate because maybe when, my update was being propagated, there was this server that went down, came back up 20 cycles later, You know, and everybody removed their stuff. I says, woke up. Oh my God, did I sleep well this evening? I have something that you don't have. Boom. You get the picture, right? So here's this lazy guy just getting up saying, hey, I got something that nobody else has. I got some news to tell you. So that's not going to work. So now I do want to get rid of these death certificates. So how do you do this? Okay, so let's just first think of death certificates propagated in a let me take the second bullet. Death certificates propagated in a finite time. That's your 20 cycles. Okay? And then I'll just, hey, I'm an engineer, not 20, I'll take 40 cycles and I'll just remove it. So even apart from the fact that there may be this lazy service, and spreads the news again, there's another problem with this. Why did you mention 20 cycles?
So I saw it probably we could calculate the amount of cycles we need for everyone to reach it.
Exactly. So you came up with the 20 cycles because of the example I just showed. There was something very important about that example.
I'm not talking about the probability one.
No, you're not talking about the probability.
Depends on the size of the network.
Who said that? Depends on the size of the network. That's it. It will be 20 cycles for that specific network. It will be 30 cycles for another network. By the way, much larger, okay? Maybe 100,000. But the problem is there's a dependency between your propagation time and the size of the network. So if you want to have a scalable algorithm, or actually to make it more accurate, a network size independent method for removing data, you cannot rely on your cycles.
But you do know the size of the network.
Provided you know the size of the network.
And you can easily solve it by if the node went down and it goes up again. Don't propagate, but listen.
No. Okay. One thing. Okay, I'll try to repeat that. You know, you could solve the solver problem, the server problem. It wakes up, says, "Hey, new world," by saying, "No, you're not allowed to propagate." You know, just start thinking about this, and you see, how do I tell that guy not to update stuff? You know, or not to send this update? And I want all of you to get in really super duper simplistic mode. Act as if you're dumb. Okay? And none of you is dumb. You know, this is an important assumption here also, and which is true, by the way. It's a valid assumption. So, but I want you to get into really, really simplistic mode. The simpler, the better. Did I mention, maybe I mentioned this once in this class. I have a very simple rule. It is extremely simple to come up with extremely complicated solutions. It is extremely difficult to come up with extremely simple solutions. But we tend to forget that because the simple solutions are so simple. So, you know, everybody could have invented that, and the answer is no, that's not true. It takes a lot of creativity to come down to something that is so simple that a teacher like me can actually explain it to you. Okay, so that's one thing. You could also try to run a global algorithm just to check if everybody has removed this stuff. That's called garbage collection, which is good, but not for 100,000 servers. Okay? Now, okay. Oh, so, yeah, I thought there was another slide actually giving the solution. So, let's try to solve your server problem. I propagated something. I had my death certificates. Everybody removed the death certificate except this lazy bum that woke up and said, "Hey, new world." Yes.
If we are associating a sequence numbering along with the death certificates or along with our original news, so is there really a need to remove the certificates? Because the later update will come up with a new sequencing number.
I really want to get rid of this death certificate. I want to really clean up my system. That's my assumption. Okay? Whether it's a good assumption, I don't matter. I just want to get rid of this stuff. Okay? It's there, and I just don't want it. It's garbage. Okay. So now I had this server wakes up, starts spreading the news.
Logging
done in our solution, having an ID, some sort of
So you got to realize what's going on. Have the server says, I got something new, spreads the update. What would you do?
you just put an ID, a unique ID to that message that you get that update,
You do a new ID to that message.
and that's it.
Why would that save the day?
Well, it can fingerprint somehow the message that you just received.
And what would be? I would probably fingerprint the message. So that means that I would have to remember something about what has been deleted.
Something, yeah.
I don't want to do that. Garbage is garbage. I want to get rid of it. So at the moment that I've cleaned up stuff, hey, I'm stateless. That's the situation I want. Okay, but otherwise, it could work. Yes.
And maybe you can use epochs. So you can start a new era and say, well, we all synchronize and we all clean up our stuff. So while synchronization will take some time, during synchronization, nobody is allowed to send any updates.
Okay.
But after synchronization, everybody agrees with everybody. And
Okay.
you have these.
Okay, so let me repeat your suggestion. We could use epochs, and then basically we go from epoch to epoch, and before entering a new epoch, everybody gets the command to clean up. Okay, that would work. But now I have 10 million servers. I don't like that. How do you do this in practice? Yes.
How would you just have a number with the next expected value?
I'm a really foolish server. If somebody tells me clean up, I clean up, I throw it away. I don't want to remember anything. How would you do this in practice?
Wait especially long time before you do that.
No, and I'm not going to wait for a very long time.
What if every message actually has a timestamp and just define a certain
Simpler. Simpler.
There, don't recreate.
What?
If it's not there, don't recreate.
If it's not there, don't recreate it?
Yeah, so you delete something and then someone says, oh hey, I have something for you, but you deleted it, so forget about it.
I have an even simpler solution. You know what you do in practice? You maintain a few labs in practice. If you think in terms of viruses, when do the heated debates start? Should we close down the last lab that has the antivirus for the virus that you suppose was actually extinguished? So what you can do, and this is a practical solution, is you maintain a few servers that maintain a record of everything that was ever out there. That is not really a big problem. You can even make them fault tolerant. And when one of these guys wakes up and starts spreading the news again, you just throw in another death certificate. You overrule him again, and that's it. It's as simple as that.
So it's some kind of append-only system which keeps. It's like Bitcoin, actually. Bitcoin also saves the entire history always.
Well, I don't know the intricacies of the intermediates of Bitcoin, but the thing that I'm saying right now is, and even with a system with 1 million servers, I can maintain one server who is always out there, who will maintain a complete history. And a complete history is just a long list of all these death certificates. If it notices, because it's just part of the system, that somebody is spreading an update that should be dead, it just throws in its death certificate into the system, and after a while, everybody starts cleaning up again, but I just, I can't come up with the English word. I compensated what this other lazy server was just producing into the network again. That's how you actually do this in practice. Yes? That particular server has to be a reliable one.
No, that's right. But since not all nodes in the system is guaranteed to get all the messages that are there in the system,
Yeah, because you don't have guarantees that everybody will get the update. I'm now talking about anti-entropy, by the way. Now, with gossiping, that's not going to work. With anti-entropy, it will work. Okay, you will guaranteed reach everyone. But that guy assumes that it can spread death certificates in no time and that they will be removed automatically after a while. Okay? And then if somebody actually pops up and throws in the update again, it will just throw in its death certificate again. Yes?
I see a biological problem there. The question is, how big is the impact of an infected subset of my whole system? And how
Oh.
can I get rid of that?
Absolutely. So so let me try to repeat your remark. I have made something. I gave an extremely simplistic approach to this. Okay, this approach may not work if the update that you're spreading is actually a nasty one. Suppose it was a real virus. Okay, and and then a death certificate may not be good enough because you don't know what kind of harm it's been doing. I'm throwing all those type of problems into the corner right now. Okay, but otherwise you would be right. But then you would probably take completely different measures. Now I'm just talking about a system of propagating normal updates, non-harmful, harmless updates, and just making sure that the system as a whole is up to date. But otherwise you would be right.
For example, if we have one node waking up like here,
Yes.
and most of the network is here,
Yes.
and we have our death certificate storage like here, and the stuff starts spreading out.
Oh, okay. Here's another thing.
Then I spread outward, and most of the network will have the wrong update.
Hold it. You're making a big. So I can't repeat this by just recording this, but imagine a spatial network. A spatial network, which is the assumption you're making, is one in which an update is spread geographically. Okay? That's basically your assumption. And geographically can also be in terms of network geography. Okay? Now I made one very, very important assumption. When you spread an update, you pick another node at random. Okay? Which means anywhere in the network. Bye-bye spatial behavior, location stuff. And then that problem will not occur. If you have spatial networks like wireless networks, believe me, you can apply special gossiping algorithms that will almost mimic the same behavior as you would see in a wired network. But it's a bit too much to explain the gory details of that. Can I have 5 more minutes? Is that okay? 5 more? And it will be a kind of it's an interesting teaser. What can you do with this stuff? Okay? Data dissemination should be clear. But here's also a very nifty application, aggregation. Aggregation is collecting data over the network. Let me put it like that. Imagine this. Each one of us starts with a random variable. Okay? And then if you and I contact each other, I take your value, you take my value, I add it up, and we divide it by 2. That means after the exchange, you and I will have the same value. Agreed? Is everyone with me? So, contact, you and I exchange values, you get mine, I get yours. No matter how many people I already contact, we divide it by 2. After the exchange, you and I have exactly the same value. Agreed? What happens in the end, if everybody does this, is that everybody computes the average. There's nothing else you can do. And the reasoning is extremely simple. If you take a look at the sum of our variables, am I affecting that? No. The total sum of all our variables will remain constant during all exchanges. Nothing changes. The only thing that I am doing is gradually making sure that everybody has the same value. That can only mean one thing. We are all going to compute the average. Agreed? Okay. So here's the teaser then. One of us, we bent klaar. One of us starts with 1, and all the others have as initial value 0. What's the outcome?
The size of the network, 1 divided by the size of the network.
1 divided by the size of the network. I just gave you an algorithm to compute how big your network is. Okay? Got it? Okay. And then tomorrow I will start with the following question. How can I make sure that I don't need to appoint exactly one of us to start with 1 and the rest with 0? Think about that. Because that's still a centralized issue, right? So now I want all of us to compute the average size of the network without knowing who was the one who started with 1. Your turn for tomorrow. Okay? I'll start with that question. See you tomorrow.